Hello, everyone. Welcome to today's live broadcast. Back to Basics for Biochromatography, Reversed Phase LC Method Development for mAbs. I'm Laura Bush, the Editorial Director of LCGC, and I'll be your moderator for today's event. We're pleased to bring you this webcast presented by LCGC and sponsored by Advanced Materials Technology. Advanced Materials Technology is an innovative product development and manufacturing company focused on improving liquid chromatography separations. After pioneering fused core technology in 2005, the Halo product line has changed previous conventional wisdom that high resolution requires high back pressure. Now in its 15th year, AMT continues to be a leader in novel superficially porous particle development, enabling high efficiency and reliability for scientists involved in both small and large molecule separations, and delivers applied solutions designed to meet specific industry challenges. Before we begin today, we have a few housekeeping announcements. First, the webcast is designed to be interactive, so we encourage you to ask questions. You can submit questions at any time by typing them in the Q&A box, and you can find that on the right-hand side of your screen. You can enlarge the slide window by clicking on the small square icon in the upper right-hand corner of that window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the webcast. And if you have any technical problems viewing or hearing the presentation, please click on the question mark Help widget in the dock at the bottom of your window. Before I introduce today's speaker, I would like to ask all of you in the audience to participate in 3 very brief polling questions. In each case, please click directly on the screen to enter your answers. So here's that first question that's now on your screen. What is your biggest challenge in mAb analysis? Lack of chromatographic resolution, runtime or throughput, sample preparation, chromatographic reproducibility, column lifetime, new method development. So once again, click directly on the screen to enter your answers. And that question is, what is your biggest challenge in mAb analysis? Lack of chromatographic resolution, runtime or throughput, sample preparation, chromatographic reproducibility, column lifetime, new method development. Give you all just another moment or two to answer that question. I can see the answers coming in. And again, you can click right on your screen to enter your answers. Waiting to see a few more answers coming in. Fantastic. We're getting excellent audience response and the replies. It's fantastic. Just wanted to hear about your biggest chromatographic challenge. All right. Well, I think we'll wrap that one up so we can move on to the next one. Let's take a quick look at the results. So it looks like the biggest challenge overall was a new method development, but we've got a lot of votes for lack of chromatographic resolution as well. Fantastic. Thank you all for taking that polling question. So let's move to our next polling question now. What is the most predominant separation technique employed for your protein analysis? SEC, reversed phase, HIC, ion exchange, or all of those techniques, SEC, reverse phase, HIC, and IEX equally? So again, you can click directly on your screen to enter your answers, just as you did last time. And that question is, which is the most predominant separation technique employed for your protein analysis? Size exclusion chromatography, reverse phase chromatography, HIC, ion exchange, or all of those techniques, SEC, reverse phased, HIC, ion exchange equally. Give you all another moment or two to keep answering that question. Again, you can click directly on the screen to enter your answers. What are you using in your lab? All right, lots of answers coming in. Fantastic. All right. Well, perhaps we can wrap that one up and let's see the answers on that one. So the number 1 answer was reverse phase chromatography, but a lot of you are using a combination of those techniques, about 35%. Fantastic. All right, let's go to our third question. What is your most predominant detection technique used? LC-UV, high-resolution mass spectrometry, light scattering detection, or all of those techniques. LC with ultraviolet detection, high-resolution mass spectrometry, and light scattering detection, all those together. So once again, you can click directly on the screen to enter your answers. And that question is, what is your most predominant detection technique used? And this, again, I think would be for your protein analysis in your lab. So again, your choices are liquid chromatography with ultraviolet detection, high-resolution spectrometry, light scattering detection, or light scattering devices, LSD, or all those techniques together, LC-UV, high-resolution mass spectrometry, light scattering devices, or light scattering detection. Give you just another moment there. Seeing a lot of great responses from our audience. All right, fantastic. Let's pull up those results. All right, so the vast majority of you, almost 2/3, are using LC with UV. We've got some decent votes for high-resolution mass spec, and a number of you using various techniques. Fantastic. Thank you all so much for taking those polling questions for us. I would now like to introduce today's speaker. We're very pleased to be joined today by Dr. Barry Boyce. Dr. Barry Boyce is the Chief Technology Officer at Advanced Materials Technologies, or AMT, in Wilmington, Delaware, in the United States. Barry Boyce completed his PhD in neuroscience at UBC in Vancouver, BC, Canada. Then he joined the DuPont Company in Wilmington, Delaware. Over the past 3 decades, Barry has enjoyed a variety of scientific, senior management, and executive roles with large corporate and smaller startup companies. In his current roles at AMT, at the University of Georgia, and at Glyco Scientific Incorporated, his focus is on improving technologies for biomolecule separations, structure analysis, and functional roles. Dr. Boyce, thank you for joining us today. Please get us started.
Thanks for having me today, and it's great to be here. Good morning to everyone if you're on my time zone here in Delaware. If not, then perhaps good evening or otherwise. So today, I've been asked to speak to you about reverse phase method development for monoclonal antibodies. Of course, many of the considerations in the discussion today will apply to other proteins as well, but the principles that we've investigated the last several years will hopefully be of use for you. Here at Advanced Materials Technologies, it's a banner year. We're celebrating our 15th year in existence. We started in 2005 specifically to bring to market superficially porous particulate materials for analytical applications. Our focus has been largely on this in the last 15 years with the continuing development of the technology to address analytical applications. Initially, we started with as shown on the timeline on the bottom of the slide, we started with a 2.7 micron diameter superficially porous particle. We've expanded this over time to include 5 micron materials in small pore, so equivalent or appropriate for small molecule applications. In 2013, we extended this technology specifically to look at materials that would be best suited to biological macromolecules, including peptides, proteins, and carbohydrates. Since that time, we've also made a smaller particle superficially porous materials, bringing to the marketplace the 2 micron SPP material, and then followed that up in 2017 with very large pore, 1,000 angstrom pore size superficially porous particles. Most recently, we've specialized this technology particularly for the expanding needs in environmental analysis. So we didn't sleep last year during our lockdown. We were quite busy bringing products to market for that need. The superficially porous particle technology is not a new concept. It's been around since the late 60s. This is the first page and first diagram from a patent application that, as you can see, dates from the late 60s. This was the conceptual development of Jack Kirkland, and on the left-hand side of this slide, you can see the cartoon depiction of a superficially porous particle with a internal solid core of impermeant silica, spherical body surrounded by a communicating freely diffusible exterior shell of microparticulate silica sol. So the idea here was that this freely diffusible outer shell would allow surface area for the interaction of materials for chromatographic separation, while the impermeant material at the center would reduce the diffusion distance and contributions to band dispersion. It took a number of years, in fact, several decades, to really reduce that conceptual development to full practice in commercially available materials that have been determined to be really useful. Again, on the left-hand side of this slide, you'll see the cartoon depiction of a superficially porous particle, this being the dimensions and specifics of material that AMT brought to market in 2006 with that outer porous shell and internal solid core, 1.7 micron for the internal pore, half micron shell thickness. In this case, we're showing a 90 angstrom pore size material. And this was found to be quite good for small molecule separations. You can see on the right-hand side, scanning electron micrograph of a particle that's been sliced so that you can see the solid core at the center of the superficially porous particle, surrounded by a porous shell that supplies the surface area needed for a high-resolution chromatographic separation. Now, we like these particles because we can make them in a relatively modest particle size, that is 2.7 micron, so that we get acceptable back pressure. There's no need to use very small particulate silicas, which means that there's a number of practical advantages, including obviation of the need for very small frits to retain the particles in a column. Because of this, they are less prone to plugging and other sample-associated limitations that you can run into in the daily use and repetitive use of a chromatographic column. But the real purpose of this particle design was that we would be able to obtain high-resolution chromatographic separations while maintaining efficiency at high linear velocities. That is, there's a flat C term in the Van Diemter relationship. There's limited band dispersion as linear velocity is increased. So we maintain high efficiency with high throughput separations. Now, this was a gratifying development, but really my personal interest as a biochemist was how can we utilize this technology to enable high performance separations for larger molecules, and in particular larger biomolecules. And in today's discussion, that will really focus around monoclonal antibodies. Well, the first requirement is clearly around the ability to have a pore size large enough to fit a larger protein molecule into the interactive surface area of a superficially porous particle. That is, to get around the restricted diffusion limitations that would result from smaller pores. In addition to the efficiency effects that result from restricted diffusion, I'll also show you some indication that there's load capacity limitations that result from insufficient pore size. So peak capacity, which is a convenient chromatographic measurement of global separation capability, has limitations caused by both kinetic and retention properties. And these are addressed by using sufficiently large pore sizes. In addition to the architecture of the particle, we need to consider the surface chemistry and what's most appropriate for reverse phase. In addition to alkyl bonded phases, which have for many years been popular materials for reverse phase separations of proteins, we've also now included an aromatic bonded phase, and the one we chose was the diphenyl bonded phase material for reasons that I'll share with you shortly. With such particles now available and demonstrating utility, we have endeavored during the last decade to look at some of the other considerations for generating high-efficiency protein separations, and in particular, the modifiers and conditions for gradient elution. That is, most reverse phase separations for proteins are going to be conducted under acidic conditions. And the nature of the acidic modifier is important, as is the organic strong solvent used for elution during gradient elution. Temperature plays a critical role in protein separations, and it is particularly noticeable on the recovery of monoclonal antibodies during reverse phase HPLC. As we get to the end of the presentation today, I will share with you some laboratory approaches that we've developed and have found useful to systematize the method development that we've used for monoclonal antibody separation. And it uses the combination of these variables that we've just discussed. So the first of these are particles and pores. What do you need for high-performance reverse phase separation of monoclonal antibodies? Well, the initial material that we brought to market in 2013 had a 400 angstrom, fairly thin shell of superficially porous material around a relatively larger impermeant central core. And this showed significant utility, particularly because it did address many of the aspects of the kinetic limitations that restricted diffusion causes for larger molecules. So it did demonstrate the need for increasing pore size. We brought to market a 400 angstrom pore size material. It was great for small and mid-sized proteins and showed some utility for larger proteins. As we continued to develop this technology, in 2017 we brought to the market the 1,000 angstrom pore size material shown on the right-hand side of this slide. This further addressed restricted diffusion limitations, showing very high efficiency protein separations, as well as improved the mass transport at high linear velocities. In other words, throughput, the ability to do the separations quickly. So this has become the best-in-class material for reverse phase separations. We thickened the shell, resulting in a larger surface area for higher load capacity, while not compromising resolution for very large protein molecules. So this has resulted in a material that has shown considerable utility. But the 400 angstrom material was clearly used for a number of important and useful applications and continues to be used today. An example of this, for example, is shown on this slide with the heavy and light chain separations for an IgG. In this case, it is trastuzumab on the left-hand side and the sigma MSQ8 antibody drug conjugate mimic, so a ADC material on the right-hand side. Almost always in our lab, we use a combination of UV detection and online mass spectrometry. And we do this for protein analyses because we would like to be able to see the greatest dynamic range we can get, which UV detectors are very good at, but we also need information on specific identities. and the ability to deconvolute the complicated mass spectra to derive what we believe to be the protein structure. So that's, of course, how on the right-hand side we're able to distinguish the various antibody-drug conjugate identities for the light chain and heavy chain variants. And in fact, the ability to couple high-resolution mass spectrometry with high-resolution separations has been particularly useful in protein chemistry. Another example, in this case, using a 400 angstrom pore size material. In this case, looking at, instead of just heavy and light chain separations, looking at an IDES, proteolytic digest of an IgG, doing such an experiment with and without the reducing agent dithiothreatol present allows us to gain particularly useful information on the variance of heavy chain and light chain fragments and to map the regions of these interactions. Of course, this requires online mass spectrometry to get really useful and informative information. That's shown in the middle part of the diagram on the left side of this slide. Now, in this case, we are actually using a slightly different modifier of the mobile phase. We'll talk about that in a little while, which is difluoroacetic acid instead of trifluoroacetic acid. And we use that quite a lot for intact protein separations. So restricted diffusion, in other words, the requirement for larger pores doesn't matter. And in probably the clearest example of this is when you take a look at IgG2s. This is data that came from a biopharmaceutical house that we were doing some collaborative work with, where they had used the method that was in the literature for looking at IgG2 thiol variants. IgG2, unlike IgG1, shows rather large-scale intact protein rearrangements as thiols interchange in the heavy and light chain, particularly around the hinge region of IgG. And you can distinguish these by mass spectrometry, but resolving them chromatographically has been a bit of a challenge. And you can see on the first panel, doing that with a 300 angstrom pore size, sub-2 micron material gave only partial resolution of the thiol variants. The use of an early superficially porous material, 300 angstrom, with a C8 bonded phase gave a little bit better resolution. When a 1,000 angstrom C4 material was employed, there's clearly a much greater resolution of the thiol variants in this IgG2 material. With IgG1s, we see this pattern continue of improved peak widths, that is column efficiency, for the resolution of larger molecular weight proteins, in particular, in this case, an IgG1 monoclonal antibody. Looking at a sub-2 micron, 300 angstrom fully porous particle material in black versus the 1,000 angstrom superficially porous particle material in green, we see not only a better peak width under identical gradient conditions, but a slight increase in retention, suggesting that more of the surface area is available for interaction, plus also greater resolution of the later eluting variants of that monoclonal antibody. We'll show some examples or additional examples of the variants one can see in a therapeutic monoclonal antibody of this sort with this improved chromatographic resolution. Now, this effect is not specific to this particular IgG1. And in fact, when we look at a larger range of IgG1s, we see that this is a general effect. Okay, so in this plot shown on the left-hand side, smaller peak width is better. Narrower peaks are clearly better. And we're comparing a 300 angstrom sub-2 micron fully porous particulate material to the 1,000 angstrom superficially porous particle material, and clearly the peak widths are better for every IgG1 that you look at. So there is an advantage to the use of a superficially porous particle with large pore size. And it is across all of the monoclonal antibodies that we've looked at. The advantage is in fact greater as you increase the flow rate. That is, that C-term effect now comes into play. What about loadability? Well, the thing about building a larger pore is that the compromise is that you are reducing the surface area of the particulate material. So this compares the loadability or load tolerance as we increase the amount of a monoclonal antibody that's been injected. We're looking at the peak width. Smaller is better. Okay? And in this case, it's a gradient elution. And we're comparing a 2.7 micron, very large pore, superficially porous material with the original 3.4 micron, 400 angstrom pore size material, and a sub-2 micron, 300 angstrom. And as you can see, when you get up to increased load, well, first of all, at any load level, the superficially porous particle material, as expected, shows greater efficiency, narrower peaks. As you begin to load up the surface, we see that superior performance is maintained across all load levels for the 1,000 angstrom material. It begins to drop off a little bit when you get up to high load for the 400 angstrom pore size material. The reason we believe that explains this is that when you talk about pore size, you're really talking about a statistical average of pore size. Clearly, in a 1,000 angstrom pore size material, that population is centered at 1,000 angstrom pore size, but there's some proportion that's a little bit smaller and a little bit larger. That's clearly the case with a 300 angstrom pore size material. Some of the pore population is too small for the monoclonal antibody to fit into. Hence, you begin to overload the surface area. Even though it's a greater surface area, it's only useful surface area if you're able to interact with it. So this is maximized as you increase the pore size. Okay. Similarly, the so-called C-term effect, or resistance to mass transfer effect. In other words, the effect of linear velocity. Clearly, there's an advantage with a superficially porous particle material, which has a shorter diffusion path. But also, with a very large pore material, you're able to more freely diffuse into and out of the particle. There's less restricted diffusion, better mass transfer. All of that results in better performance as you get to high linear velocities. In this case, in many cases, we're actually seeing people use superficially porous materials add up to 0.75 to a mil per minute in a 2.1 millimeter ID column with minimal effect on column efficiency. Okay, so with such materials now available, are there things we can do to improve protein separations by reverse phase? In other words, what are the use conditions that we could take advantage of? We'll consider global phase manipulations, bonded phase manipulations, and operational temperatures. And then we'll talk about how these different parameters can be used together to improve separations of monoclonal antibodies. Okay, so the first thing that we looked at, and this is, I'm not going to go into a great deal of detail on this because this work's a few years old now. We looked very carefully at the acidic modifiers that can be employed in reverse phase separations. And there's a variety of requirements that we would place on utility for a reverse phase acid modifier. Of course, UV transparency, support mass spectrometry, good efficiency in electrospray ionization. as well as low toxicity, low cost, high purity, et cetera. From a long list of materials that we looked at systematically, we selected 3 that are obvious here because they've been used for a long time, and 2 additional. The 2 additional ones are difluoroacetic acid and 3-fluoropropionic acid, or propanoic acid. These were ones that as well supported reasonable protein solubility. So we've used these in the lab. The one that we've used the most in terms of the more specialized or newer materials has been difluoroacetic acid. And we've used it over an extended period of time now, about 7 years, with no untoward effects on our chromatographic instruments, the column materials, or our mass spectrometers. So why do we like DFA? Well, here's probably the easiest way to explain this is looking actually at a peptide separation, where the effect is most obvious. A little bit less obvious in protein separations, clearly obvious in peptide separation. This is a comparison showing the electrospray ionization in the presence of 10 millimolar difluoroacetic acid, formic acid, and trifluoroacetic acid. And what we see is that difluoroacetic acid does cause some ionization suppression relative to formic acid, but nowhere near as bad as what you get with trifluoroacetic acid due to its strong ion pairing with basic amino acid side chain. There's some other less obvious effects that favor the use of DFA over TFA. The first is it's easier to get rid of. We can wash it out of an LC-MS system very quickly, switch over from difluoroacetic acid to formic acid in an LC-MS with minimal trouble. Doing that with TFA requires pretty extensive flushing and regeneration of the LC-MS system. So we like DFA. We use it quite a lot. It's also quite good in UV detection. So this is a comparison showing monoclonal antibody separation for the 3 most commonly used acidic modifiers: formic acid, difluoroacetic acid, and trifluoroacetic. Formic acid is a problem with intact protein separations, even at high temperature. Until you get above about 0.25%, you really begin to see significant recovery problems for a lot of monoclonal antibodies and peak shape. And this is shown on the top panel. Comparatively, difluoroacetic acid with a much lower pKa and trifluoroacetic acid, again, with a much lower pKa, better supports good peak shape for intact monoclonal antibody separations. You'll also note, comparing DFA and TFA, that the peak widths are similar. The tailing factors are not terribly different. So in other words, they're substitutable acids. Now, in reality, the electrospray ionization is not tenfold different, better than what you get with trifluoroacetic acid. So formic acid absolutely is still the best to support high efficiency ionization in electrospray for mass spectrometry, but DFA is clearly a little bit better than TFA, and as I said, has a number of convenient features, not the least of which is we can get rid of it quickly. Okay, bonded phases. Well, in addition to the classic alkyl bonded phases, C4, C8, C18, there's good reasons from the literature and from history and from collective wisdom from protein chemists that the aromatic bonded phases are useful for protein separations. And we've followed up on this with the development of a diphenyl aromatic bonded phase material for use in protein separations. If you look back about 15 years, the diphenyl material was favored for certain protein applications. The problems that were run into is that they weren't particularly stable or reproducible. These problems have been addressed the last several years. The trick to it seems to be you need to get really high density coverage for the diphenyl bonded phases. We've been able to do that by pushing the reaction very hard to 2.7 micromoles per meter squared on the surface for the diphenyl. That works out to about 5.5 micromoles per meter squared of aromatic ring. Under these conditions, not only can you make the materials reproducible, but also they're surprisingly acid stable in a manner comparable to so-called sterically protected bonded phase materials. So we found this aromatic bonded phase to be quite useful, and we've included it in our offerings with the 1,000 angstrom pore size material, superficially porous particles, to supply some selectivity options relative to the classical N-alkyl type of bonded phase. This is a comparison of that aromatic and 2-alkyl bonded phase materials for the separation of a standard mixture of proteins, from relatively small ribonuclease to somewhat larger enolase. What I'd like to point out is that if you look at the retentivity of these three different bonded phases, of course, it would be diphenyl is the least retentive. C4 would be, for small molecules, would be the next most retentive, and the C18, as many of you are probably aware, would be the most retentive material. When you look at protein separation, globally, they look pretty similar. They all clearly support good retention for protein separations and gradient elution. There are subtle differences in the selectivities as you compare this aromatic bonded phase to the 2-alkyl bonded phase. There's not a global shift in retention when you think about a whole mixture of proteins, but there is a number of subtle selectivity differences as you compare these three different bonded phase types. So having the option of more than one bonded phase does supply some selectivity differences. They are subtle, relatively speaking, but they can be useful when you need to start pulling apart very similar sequences. The second thing that occurs in this comparison is that you're not seeing big differences, or really any appreciable difference in bandwidths. In other words, as you use different bonded phase materials, you do have some selectivity options, but it's not at the expense of column efficiency or chromatographic solution. Okay, what about when we look at monoclonal antibody separation? Well, this is a comparison using trastuzumab as the analyte, so a therapeutic monoclonal antibody, looking at the aromatic diphenyl bonded phase, a C18 and a C4, and on the bottom compared to a fully porous particle, 300 angstrom material. Now, the superficially porous particles clearly give you better peak width. What you do see is an often repeated pattern, which is the diphenyl, even though it's the least retentive for small molecules, is the most retentive for a monoclonal antibody under these reverse phase conditions. Frequently, the order is looking at bulk retention is diphenyl is greatest, followed by C18 and then C4. Why that should be, I have no idea, but that's what we reliably see for many monoclonal antibodies. There's clearly some subtle selectivity differences that you see when you look at the smaller variants of these protein sequences. That is, the peaks that precede the main or the bulk of the monoclonal antibody present, as well as the trailing peaks. The patterns look a little different, and they're resolved to a different extent across the three different phases. Okay, so we've shown that there's some selectivity differences in bonded phases. We've shown that there's some options in terms of mobile phase modifications. Now what I'd like to do is start putting together these elements of separation to see how they interact. In other words, the interaction between temperature, bonded phase choices, and mobile phase characteristics, and specifically for the separation of monoclonal antibodies. Well, the first thing that you'll note is that, and this has been known for a very long time, is that with intact protein separations, temperature is critical. And with monoclonal antibodies, this is, if anything, doubly the case. This is separation, in this case, using the C4 bonded phase, superficially porous particle material, 1,000 angstrom, looking at ipilimumab and nismab as a function of temperature. So at 80 degrees, you get a full recovery for both of these monoclonal antibodies under these typical PFA-containing mobile phase conditions when you see them. As you decrease the temperature, you begin to see monoclonal antibody-specific loss of material. In other words, at 60 degrees, you're clearly losing more of one monoclonal antibody compared to. By the time you get down to 40 degrees, you're having significant recovery problems. We've looked at a large number of monoclonal antibodies trying to sort out these effects in terms of recovery and the effect of bonded phase and temperature. And this is a complicated slide, but I'd like you to first focus on the left-hand side where we're looking at a comparison of recovery using acetonitrile in a mobile phase and varying the temperature. Okay, so this is with a gradient of acetonitrile, varying the temperature, looking at recovery. Okay, and we're looking at two different columns. In black, the diphenyl column. In blue, the C4 alkyl column. By the way, we see very similar recovery on C18 and C4. Okay, so we've also included two different monoclonal antibodies here, trastuzumab and nismab. And what you see is that you need to be up. The acetonitrile is your organic modifier. You need to be up above 70 degrees to be confident that you're getting full recovery. It varies by monoclonal antibody. Clearly, the diphenyl, so the aromatic bonded phase, allows you to operate at a slightly lower temperature while still maintaining high recovery. Now, switching to the right-hand side, we wanted to compare those recoveries with acetonitrile to what happens when you use an organic modifier that uses a mixture of acetonitrile and protic solvent, so an alcohol. In this case, it's a mixture, 50-50 mixture of acetonitrile and propanol. And what you can see is that there's a shift towards the left-hand side, that is lower temperature, when you use an organic strong organic solvent, that is acetonitrile and a protic solvent, an alcohol. We see this somewhat independent of the exact nature of the alcohol, in other words, whether you use the isopropyl and propyl or even butanol, or the exact concentration of the alcohol. Having alcohol in there essentially results in higher recovery at lower temperature, favors the aromatic bonded phase, but you clearly see it with the N-alkyl bond. And we see it regardless of the exact concentration of the alcohol that's added, the exact proportion of it. We compared this with different concentrations of alcohol and acetonitrile. And we see that effect. As long as you've got 10 to 20% of the alcohol in there, you see this effect. Okay, so that's great. You need to operate at elevated temperatures. You can bring the temperature of operation down a little bit if you use an alcohol acetonitrile mixture. That's useful to know. And you can even bring it down further with an aromatic versus an alkyl bonded phase. Why do you really care about temperature? Well, elevated temperature is not without risk. It's important to get full recovery, but we have seen examples of monoclonal antibodies where we see a temperature-dependent accumulation of artifacts that are due to the chromatographic conditions. In other words, in this case showing mAbs, which is one of the more sensitive monoclonal antibodies where we've seen this, we see a second peak here shown with the asterisk. It precedes the main peak, and as we've investigated this, the accumulation of that early eluting material is time and temperature dependent. As we leave it longer on column with a delay experiment, we see accumulation at 60 degrees, we see a more rapid accumulation at 80 degrees temperature of operation. And we see this whether we're using difluoroacetic acid or trifluoroacetic acid as the modifier. When we investigated the nature, the identity of this material, it was not terribly surprising that we observed that this is a methionine sulfoxide. Okay, so we do have a time and temperature dependent accumulation of a methionine sulfoxide, and that means that as we go to increasingly higher temperatures, we must remain sensitive to the fact that there are these chemical processes that can go on, and not surprisingly, they are time and temperature dependent. Okay, so how do we put these things together to develop useful methods? And we've essentially developed two strategies that we've used in the lab a lot. A column-based approach to optimization, or a gradient and mobile phase dependent approach to method optimization. This example on the screen shows the column-based approach. So what we do is we take different bonded phases. In this case, we're doing an IgG2 separation. We want to pull it apart as much as possible to look at the isoforms. We compare three bonded phases at a couple of different temperatures, and we pick which one we think looks best at pulling apart the variants. So in this case, it turned out to be the C4. We adjusted our gradient start and end conditions to get it towards the middle of our chromatographic retention window. Okay? And then we optimized for temperature and gradient slope. And under those conditions, we're able to pull that rather complex mixture apart effectively. Okay, for those who are interested in the inner conversions of IgG2, there's a number of references shown here. If you contact us, we'll point you to the literature on that if you have further interest. The other approach that we use is a temperature mobile phase-based optimization. In this case, we're using a fixed bonded phase, the diphenyl. We initially compare temperatures, look at which temperature better supports resolution of the variants of IgG1 in this case. So this is trastuzumab that we're using. We selected 60 degrees as looking the most promising based on the pattern of these isoforms that are eluting. We then somewhat adjusted the gradient conditions to get us to the center of our retention window and looked at optimization with respect to the amount of that alcohol acetonitrile mixture, and as well the use of difluoroacetic acid versus trifluoroacetic acid. Okay. And when we now finish that optimization for mobile phase, gradient, time, and flow, we end up with panel C, which is well-resolved variants. These are isobaric or very nearly isobaric variants in this therapeutic monoclonal antibody, and we're able to sort through what exactly these variants are. Okay, to do that, you actually need to use some additional labeling experiments. I don't have time to go into that right now. Those of you who are interested, please download this information or contact us, and we'll get you the work that we've done in collaboration with a number of other people looking at the use of maleimide reagents to sort through these largely sulfhydryl or thiol based variations that are common in therapeutic and non-therapeutic monoclonal antibodies. Okay, so we've extended this recently with an additional bonded phase that we've just described in the literature. This uses a more polar bonded phase material, the trifluoroacetamithyl, a sterically protected material, and this has recently come out. If you would like a reprint or further pointer to that, please let us know. And with that, I'll summarize. So improving protein separations, in particular monoclonal antibodies, is really a function of both the material you're using as well as how you use it, that is the mobile phase, and operational conditions, particularly temperature. Superficially porous particle materials have clearly met the promise of improving resolution of protein separations. We've extended this by bringing to market a number of different bonded phases that allow selectivity manipulation. As we've been able to get higher resolution separations, we're able to now acquire a different approach to optimization of high resolution monoclonal antibody separation. And I'll wrap up by acknowledging a number of contributors to this work at AMT, at the University of Georgia, as well as in the biopharmaceutical industry. And I would like to thank these people for the work that we've undertaken with them, as well as the support of the NIH for aspects of the work. And I'd like to thank you for your attention today, and I'll stop there.
Thank you very much, Dr. Boyce, for that. Thank you very much, Dr. Boyce, for that excellent presentation. It is now time to begin the question and answer session. So as a quick reminder to all of you in the audience, if you'd like to submit a question, you can do that by typing it in the Q&A box, and you can find that on the right-hand side of your screen. All right, we've had a few questions coming in. So here's one. We've seen some methods in which the mobile phase contains blended buffers, such as TFA and FA. Can you share any experience or recommendations in that regard?
Yeah, we've looked at that pretty carefully a few years back. So the advantage of that is that if you can reduce the amount of TFA, certainly you're going to get less ionization suppression. And you really have a competition going on between a weak acid, which is formic acid, and a fully ionizable acid, trifluoroacetic acid. So there's a compromise there, essentially, that occurs between how good is the chromatography versus how much electrospray ionization efficiency you can give up. And it's tricky with respect to what's going to be good enough in terms of the chromatography versus what's going to be good enough in terms of loss of signal due to the addition of trifluoroacetic acid. Up until DFA began to emerge, there was really not a lot of other options. So we've found some limited utility in it. Quite frankly, I never use it on my Orbi traps, for example, because getting rid of TFA is a bit of a chore. So we tend to just use DFA instead.
Why does low temperature cause low protein recovery?
Ooh, that's a complicated physical biochemistry question, and it's been addressed in a few different ways with model systems. It's not clear to me what that is. There could be some aggregation going on, resulting in essentially stuff sticking in pores. If you don't have sufficiently high temperature, some of it is probably solubility or aggregation related, solubility related. Clearly, with the number of domains present within a monoclonal antibody, there's all sorts of opportunity for surface interactions that will lead to aggregative phenomena. When this has been examined using model systems by others, not by me really very much at all. I would say that there's clearly, you can never forget that you've got a lot of active surfaces going on in a reverse phase separation. You have the reverse phase bonded phase material, you have protein-protein interaction going on, and what you'll see when you get low recovery is you'll see ghost peaks on subsequent blank injection. So clearly the stuff hasn't disappeared. We can't create or destroy matter, but it's lost somewhere in the chromatographic, the relatively complex chromatographic surface.
Okay, here's another question. I usually run my separations at 0.2 to 0.3 milliliters per minute. If I move to these columns, what flow rates should I operate at, and how would it affect the resolution?
So with a superficially porous particle material, and with a sufficiently large pore size, you can operate at a significantly higher flow rate than what has typically been used. Say for a 2.1 millimeter ID column, that's typically around 1/4 of a milliliter per minute. And we've seen methods that have been developed by people who are operating at 3 to 4 times that flow rate, so up to 0.75 or even 1 mil per minute. It's really a function of, do you have an instrument that can, depending on the temperature, that will tolerate the back pressures? And do you lose much resolution? The answer is not much. At 0.5 mil per minute to 0.6 mils per minute, you're going to need to look very carefully in order to even qualify the loss of resolution for most protein separation. So feel free to turn up the flow rate. You'll get faster analyses. That's actually a good thing.
Great. For the 1,000 angstrom or any halo column, what do you recommend for the effective and simultaneous separation of LC, HC, and intact IgG1? I'm sorry.
Yeah, we've seen a number of published and useful examples of this using 400 angstrom pore size material, but personally, most of the work I do now is with 1,000 angstrom pore size material, and the reason for that is that it just allows me a wider dynamic range if I'm using a relatively low sensitivity. So I can do that semi-preparatively or lab scale preparatively, or I can do that with very high sensitivity detection with the mass spectrometer. So I tend to orient towards the 1,000 angstrom material more now. There are people who swear by the methods that they've developed with the 400 angstrom pore size material. So there may be some personal preference or specific assay considerations there, but the 1,000 angstrom is our go-to material. And generally, we start with the diphenyl or with the C4 and then adjust from there.
If I can sneak in one more here. Is the thiol isoform a critical quality attribute for therapeutic mAbs? Is the amount of acidic and base variance a more important CQA for purity assessment?
At this point, what's going on in thiols, what's going on in sulfhydryl groups and monoclonal antibodies, therapeutic monoclonal antibodies, is an active area investigation by a number of biopharmaceutical houses. And there's some, really important data that I've seen in the last year come out of the group at Genentech and elsewhere, where I think there's more attention being paid to this because there may be quality attributes associated with it, but I don't think they've been fully explored. Clearly, looking at acidic and basic variance is something that has been appreciated for a longer period of time. Until recently, sorting through thiol variance has been really problematic. Not good chromatographic approaches and fairly limited mass spectroscopic approaches. That's clearly an area where there's just much better methods emerging now. So is it critical from the regulatory point of view? Not yet. Will it be in the future? Quite possibly. I think that's a chapter that's not completely written.
All right. Well, with that, we're going to have to wrap up. Thank you very much, Dr. Boyce, for your excellent talk and for answering all those questions.
Well, thank you for having questions.
And indeed, I want to thank everyone in the audience for attending and participating in our event today. And I'd like to thank our sponsor, Advanced Materials Technology, for making today's webcast possible. We'd like to ask everyone in the audience to participate in a brief survey from our sponsor, and you can find that on the right-hand side of your screen. You'll receive an email alerting you when this webcast is available for replay. We invite you to forward that announcement to your colleagues who might have missed today's live event. We hope to see you all next time. Goodbye.